Sine is a periodic function. Its period is what? 2 pi. So yeah, that's just minus sine t. Yeah. Hooray! Now we have things we can take the Laplace transform of. So here we go. 1 over s squared plus e to the minus pi s times minus 1 over s squared plus 1 minus 1 over s squared minus pi over s plus e to the minus 2 pi s e to the 2 pi divided by s minus 1 minus 1 over s squared plus 1. There you go. Now, if I let us get all the way through today without solving a differential equation, I would feel bad. Right? So I think we have about 10 minutes left or so, right? So I think it's probably just about enough time for me to hurry through an example. So since you guys are tired at this point, it makes sense for me to pick up the pace, right? Let's see here. I think it's important to go slow through the discontinuous stuff at the start. I could have shown you 2 examples fast. I decided to show you 1 example slowly. All right. But let's do a finishing example here. Let's put all the pieces together, and let me show you how we can play and solve something a little bit interesting. So, example 17. Let's work on solving let's see here, y prime prime plus y equal to u of t minus 3, all right, where y of 0 equals to 1 and y prime of 0 equals to 2. We have everything we need to solve this problem now, all right? And this is a problem we couldn't solve before without a lot of work, right? Because this has a discontinuous forcing function. It's 0 all the way up to time 3 when it switches to 1, right? Okay, so here we go. We take the Laplace transform of the problem. So that gives us s squared, big Y, minus, man, I can't remember. You guys tell me, what do I do next? Is it 2 or 1? S times what? S times 1? All right. Minus 2, and then plus big Y. What's the Laplace transform of the unit step function? So this should be what? E to the minus 3s times the Laplace transform of 1, right? By the theorem, which is what? So yeah, the Laplace transform of the unit step function is just e to the minus 3s over s in this case. All right, so we've got ourselves s squared plus 1 times big Y is equal to 2 plus s plus 1 over s times the exponential, e to the minus 3s. All right, so we can solve for big Y. What does it give us? So the first piece here is not too bad. It's kind of a tamer version of our example 3 from today. I mean, the first piece I can inverse transform just by looking at it. It's 2 times sine t plus cosine t. That's the inverse transform of the first piece, right? This piece inverse transforms to twice cosine plus sine, twice sine plus cosine t. This, on the other hand, I don't know what to do yet. I'd like to use Hector, but if this is h of s, right, it's not quite in the right format yet. I don't know how to take the inverse transform of that yet, do I? So let's call it h of s for the sake of keeping with my lingo over there for a moment. These letters are not written in stone. In fact, using h here is probably bad form because h is often used for the transfer function, which has a fixed and independent meaning in engineering in your book. Anyway, more about that some other day. A over s plus bs plus c over s squared plus 1, right? Partial fractions. This gives us 1 a times s squared plus 1 plus s times bs plus c. I think I'll use I'm going to use equating coefficients paired with evaluating at a specific value. S squared, I've got a plus b. With s, I've got c. The constant term, I've got a, right? Is that it? Oh, this one's kind of funny. So s equal to 0 is the natural thing to plug in, but it's also going to give us the same equation as the constant term, right? What does the constant term give us? The partial fractions algebra here is pretty easy, right? So s squared, s, and I should do it the other way, making my life easier. 1s and s squared. What's 1? 1 equals to a. Sorry, I thought that was funny. S0 equal to, what's the coefficient of s? C, yeah. And then s squared, what's the coefficient of s squared? Over here I got 0. Over there I've got what? A plus b. Therefore b is minus 1. A is 1, c is 0. All right, excellent. So if you don't mind, I'm going to keep working here. Y, I mean, if it was your work, I hope you would work down the paper as opposed to over. I mean, there's better ways of organizing it. Stupid board work. All right, 2 plus s over s squared plus 1. And then we just figured out that h of s is, in fact, what is it? It is 1 over s, right? Minus s over s squared plus 1. Right? And that's times e to the minus 3s. At this point, I can write the answer down using Hector. So take the inverse of Laplace transform and use the Hector formula. We get y of t. This piece gives me, as I said before, 2 times sine t plus cosine t. This here, I'm supposed to do plus something times u of t minus 3. What's that something? It's supposed to be h of t minus 3. So just to give you a little fine print here, if this is h of s, right, that tells me that little h of t is 1 minus the cosine of t, taking the inverse transform. So by the Hector formula, I put 1 minus the cosine of t minus 3. There's nothing to do to the 1, right? Evaluate the constant function 1 at t minus 3. It's still a constant function 1. And there you go. That's the answer. You should notice, like, the beauty of this technique is, while the force is defined to be different before and after time 3, we just do one solution for the whole thing, right? The discontinuity of the forcing function is somehow wrapped up in the Laplace transform. And also, again, just to not, I should keep selling this, it wraps the initial conditions into boot. So here you go. I mean, this is how basically what happens is, to start with at time 0, this is the response to the initial conditions. It's like 2 sine t plus cosine t, right? And then after that time, you start pushing on the thing with a force of 1 past time 3. And after that, the motion's still sinusoidal, but with a different amplitude, but with the same frequency as it happens. So, trying to think of this could be something like if you had a spring, for example, hung in an elevator, and then all of a sudden at time 3, the elevator started accelerating upward. It would put a constant constant acceleration force on the spring. This would be the sort of formula you'd get. So anyway, we will do more of these tomorrow. I still need to show you guys what's called the convolution theorem. Convolution is another tool in the inverse Laplace transform machine. It has to do with taking the you can find inverse transforms of functions that we don't really have the technology to deal with at the moment using this thing called convolution. But as usual, it comes at the cost of some unfortunate and rather hideous integration. Thanks, guys.